Hello everyone, this is the second video of the topic permutation and combination. If you have not watched the first video, then please go and watch because some of the topics are already explained over there. So let's continue. Number of derangements means number of permutations in which n objects can be arranged such that none of them occupies their original position. Suppose there are some envelopes numbered 1, 2, 3, 4 and there are some cards on which there are numbers 1, 2, 3, 4. You have to put the cards in the envelopes such that the number and the number on the card and number on the envelope should not match. Means one can go in 2, 3 or 4 but not in its original position. Derivation of this little bit lengthy, so the formula is directly written here. Number of ways to do this is equal to 4 factorial times 1 minus 1 upon 1 factorial plus 1 upon 2 factorial minus 1 upon 3 factorial plus 1 upon 4 factorial, which is equal to 24 multiplied by 1 minus 1 upon 1 plus 1 upon 2 minus 1 upon 6 plus 1 upon 24 equals to 24 minus 24 plus 12 minus 4 plus 1. 24 gets cancelled out and we have 9. So there are 9 possible derangements for this particular example. Till here we have covered mostly the important topics of permutations. Now we will come to combination. Selection of R objects out of n distinct objects. Suppose there are some numbers 1, 2, 3, 4 up to n and we have to select, we just have to select R out of these. So how it is different from permutation? Here order doesn't matter. Means if we take 1, 2, 3 and if we take 2, 1, 3, then both of these will be treated as same. In the permutation, the thing was like, suppose there were certain R places. So first place, to fill the first place we have n choices, to fill the second place we have n minus 1 choices, to fill the third place we have n minus 2 choices, and in this way we had n minus r plus 1 choices for the last place, and it is equal to n factorial over n minus r factorial. And these are the number of permutations, not combination. These are number of permutations. In case of combination, as it is written that 1, 2, 3, 2, 1, 3, 3, 1, 2, etc. For this particular case here, 6 means 3 factorial. 3 factorial of these permutations will be treated as 1 in the case of combination. Similarly here, in these permutations, there will be a pair of R factorial permutations which will be treated as 1 in a combination. So for the combination, to select R from n, number of combinations is equal to n factorial over n minus r factorial times r factorial, which is also represented as NCR. NCR is equal to NC n minus r. How? NC n minus r is equal to n factorial over n minus r factorial times n minus r factorial, which is equal to n factorial over n minus r factorial times r factorial, and it is equal to NCR. So both of these are same. Now if NCX is given equal to NCY, then it is not necessary that x is equal to y. Here is a possibility that x is equal to n minus y. For example, if 20C11 is given equal to 20 CR, and we have to find the value of R. Then R may be equal to 11, or R may also be equal to 20 minus 11, that is 9. So R has these two possibilities. Pascal's rule. There was a theorem in the permutation also which was like this. So let's discuss this. 1, 2, 3, 4 up to n plus 1. Suppose we have these n plus 1 objects, and we have to select R from these. We have to select R from these. Suppose we divide this selection in two different cases. In the first case, we will take a particular object from these, like suppose 4. That in first type of case, we will definitely select the 4. That if we are making a combination, 4 should be there. And in the another type of case, a 4 should not be selected. Means none combination should be there in the cases in which 4 is there. So in how many ways can we do it? From these n plus 1, we don't have to, we must select 4. So 4 should be selected. So let's first select 4. Suppose we are making any combination and we selected 4. Now how many selections we have to done? From the remaining n, we have to select R minus 1. So how many possibilities are there? N, C, R minus 1. Now let's see the case of let's see the case in which 4 should not be selected. 4 should not be selected means from the remaining n. From the remaining n, we have to select R. Last time it was R minus 1. Why? Because 1 was already selected and remaining R minus 1 were to be selected. But this time we need to select R because none of the object is still selected. So total possibilities and the ways in which R can be selected from n are NCR. From n plus 1 means n plus 1 CR. So on adding these two, we will get it equal to n plus 1 CR, which is written in the rule. All possible selections out of n distinct objects. Okay, so here n distinct objects are given, and you have to do some selections. Now first question which comes into mind is how many? Means till now we are discussing that we have to select R from n distinct objects, but this time R is not given. So first question which comes into mind is how many objects should be selected. It is given all possible selections. Means first of all we have to answer this question. Means how many selections can be done? We have to take all possible cases. Means 0, we have to take the case of 1, we have to take the case of 2, we have to take the case of 3, means when R is equal to 1, when R is equal to 2, when R is equal to 3, and all possible cases up to R is equal to n. Okay, so one by one we will see all these. In how many ways we can select 0 from n? It is NC0. In how many ways we can select one object from given n object? It is NC1. In how many ways we can select two objects from the n objects? It is NC2. And in this way, the last case is NCn. So these are the number of ways in which all possible selections means these are all the possible ways of selecting something from n objects. Okay, there is another method also, method 2. How? Since we just have to select something, okay, n objects are given and we have to just select something. So what are the possibilities? We can select, we have two choices to select one. Either we can select it or we will not select it. For 2, either we will select it or we will not select it. In this way, for every element we have two choices. Either we will select that or we will not select that. Hence the total number of possible selections are 2 raised to the power n. Here 0 is also included, means a case is also included in this in which none of the object is selected. And if it is given, it is necessary that you must select at least one object, then we will subtract 1 from it. Now we have calculated the same thing in two ways, and that's why both of these must be equal to each other. These are equal. Selection of R objects out of n identical objects. Here the word identical is given. Sometimes we get confused in the different questions that what is the meaning of identical, and sometimes we can't distinguish that how to approach this question, since we get confused between identical and distinct objects. So these concepts should be clear. Suppose there are 10 green balls. 10 green balls are given here, and we have to select 3 of them. In how many ways can we do it? Actually, we can do it in exactly and only one way. Why? Because since all these objects are distinct, so if we select these 3 or if we select these 3, both these cases will be treated as same, because after selection there will be no difference between these two cases. Why? Because there will be no difference between these two cases. Why? Because the objects are identical. That's why the number of ways to select R objects out of any n identical objects is 1. Second is like all possible selections out of n. Here also first question arises, how many objects should be selected. So first of all answer this question. We have to take all possible, means we have to count 0, then we have to count for 1, then we have to count for 2, and for all these possibilities number of cases should be added. So in how many ways we can select 0 objects out of n identical objects? That is 1, just explained here. Another one is also 1, next is also 1. Okay, why? Because all are identical, so selecting different trying to select different objects is not possible. So how many are there? 0, then 1, then 2, then 1 for 2, then 1 for 1, and then 1 for 3, and up to this 1 for n, and in total we have n plus 1. All possible sections of n1 identical objects, n2 identical, and like so on, and n distinct objects. So here something like this is given. Suppose there are red balls, n1 red balls, then we have n2 green balls, and in this way some more identical objects are there, and then n balls of each distinct color. N balls just of each of the distinct color. Okay, so in how many ways we can select something? So selecting from the first n1 red balls, how many possible sections are there? Either we can select 1 red ball, or we can select no red ball, or we can select 2 red ball, or 3 or 4, and in this way we have n plus 1 possibilities to select red balls. For the green we have n2 plus 1 possible ways to select anything from these given green balls. In this way, if a certain more of the identical objects are given, then we will take n3 plus 1, n4 plus 1, n5 plus 1, and so on, and at last n objects are distinct. So for distinct, if we are selecting these two, or if we are selecting these two, then the cases will be different. So here we will apply n 2 raised to the power n, because we have choice. Either we can select this or not, either we can select this or not, or either we can select this or not. In another way, you can think that there are n1 identical objects. In this way you can select that there are 1 identical object, then next is 1 identical object, then next is 1 identical object. So as we are taking n plus 1, n plus 2, you will take 1 plus 1, 1 plus 1. Like this also you can think there will be 2 raised to the power n over here. Now we will discuss some special uses of NCR. Number of lines by n points, out of which m are collinear. Suppose in space some points are given which are not collinear, means no 3 of them lie in one line, like some points are given, and then there are certain points, m points, which are collinear. Okay, m of these are collinear, and in total n points are there. We have to find how many number of lines, how many minimum number of lines we should made such that they pass through all these points, they cover all these points. If we select any 2 point, any 2 points. If we select any 2 points, like if we selected this and this, then we can make a line passing through both of these. In this way, if we select this and this, we can make a line passing through this. And in this way, if we select any two, means in how many ways we can do this? In NC2 ways. NC2 ways we can select 2 points and then we can make a line passing through them. But look at these M collinear points. Suppose we selected this and this. In this case, line will be this. If we selected this one and this one, then also we will get the same line. On selecting this one and this one here, we will get the same line. Means if from these M points we select any two, MC2, we will get the same line. So we have to count these MC2 ways just as one way. Means we have to subtract these MC2 ways. If we subtract all of these M2 ways, then this line will be will get unselected, or this line will not be counted, but we have to count it at least once. So we have to add 1, and these are the number of possibilities. Number of diagonals of a polygon. Suppose this is a polygon by having n points, n vertices, okay, and we have to select a diagonal. So we have to make a diagonal. So from these, if we from the vertices of this diagonal, if we select any two of the vertices, then we will get a line segment like this or this or this or this, etc. Okay, so there are NC2 possibilities for a line segment, but for a diagonal the points should not be adjacent. Means there are possibilities that if we select 2 points in 2 vertices and the vertices are adjacent, and in that case it will not be a diagonal, it will become a side. So means here if it is an n-sided polygon, so there will be n cases which will not be in the diagonal category. So that is why we will not take those cases. Now we have n factorial over 2 factorial times n minus 2 factorial minus n, which is equal to n times n minus 1 over 2 minus n. N is taken common, we get n minus 1 over 2 minus 1, which is equal to n minus 1 over n minus 3 over 2. Number of rectangles in a rectangle of size L cross B. What the question is asking, say this is a rectangle, and in this rectangle we draw some lines like this, and here its size is L cross B, means this these partitions, the side which divided, the length, the number of parts in which the length is divided is L, and the number of parts in which width is divided is B. Number of rectangles, we have to find the number of rectangles. So isn't it easy? Isn't it L cross B? No, actually here is we can see a rectangle over here also. We can see a rectangle like this also. We have a rectangle like this also. Means we have to find all the possible rectangles which are which can be made by combining some of these rectangles. So that will also be taken as the case of another rectangle. So in how many ways we can do it? So what approach we apply? What approach can be applied for this question? We will find the number of ways for base, or more precisely for breadth, and number of ways for length. Means what I am saying, suppose we selected a base here, breadth here like this. Suppose we selected this line segment, this part for the width, and then we selected this part for the length. So in this case we get this rectangle from here, which is just under that length and just in front of that width. And for any of the length, any of the part for length and any part for breadth, formation of this rectangle is possible. So if we find in how many ways we can make this width and in how many ways we can select this length, then we can find the number of rectangles also. Let us see. For the selection of breadth, we have to select any two of these points. Any two of these points, if we select, we will find we can make a possible breadth. Means b plus 1, out of b plus 1 points we have to select any two. And similarly for the case of length, from these l plus 1 points we have to select any two. So l plus 1c 2. These are the number of rectangles. Number of squares in a rectangle of size L cross B. Suppose there is a rectangle and this time we have to select a squares, means its length and width should be same. So the square of maximum size which can be selected is the square of side B, means this, right? This square of maximum size can be selected. Next square is just here, this one, and then the next one is like this. Okay, just a square of smaller size, square of just small size is here, this one. How many of such rectangles, how many of such squares can be taken from here, then here, then here? See, if we talk about this 1 2 3 4 5 6, this particular case of 6 by 1 2 3 4, then the squares of size 4, how many squares of size 4 can be selected? Just 3, as we have just seen. Plus how many squares of size 2 can be selected? This was of size 4, then how many squares of size 3 can be selected? 1 2 3, then 4. Okay, 4, and similarly 4 just below these multiplied by 2. How many squares of size 2 are there? If you count like this, you will get it 5 times 3, and square of size 1, they can be clearly seen 6 cross 4, and the first case was 3 cross 1. So in this way, for any general type of rectangle also we can find the total number of squares. This is how the question of for squares is different from the question of rectangles. Maximum number of regions into which a set of n coplanar lines divide the plane. There are certain questions given on the screen. You can try these by yourself. Divisors or factors. Suppose a number is given to us like 48, and we have to find we don't have to find, we have to find the number of divisors of 24. For this, first we will factorize 24. So 24 can be written as 2 times 2 times 2 times 3, which is 2 raised to the power 3 times 3 raised to the power 1. Now suppose we have to take a random factor of this 24. So in this factor 2 may be present, in this factor 3 may be present, in this factor 7 may be present. No, 7 is not possible. Why? Because 7 is not present in the prime factorization of 24, so it is not possible in any of the factor also. Okay, so only 2 and 3 are possible. Now different powers are possible, like 2 to the power 0 is possible, 2 to the power 1 is possible, 2 raised to the power 2 is possible, 2 raised to the power 3 is possible, 4 is possible. No, wait, 4 is not possible. Why? Because if we take 4 here, suppose we made a random factor like 2 raised to the power 4 into 3 to the power 1, it will not divide 24. It do not divide 24, so it is not a divisor. Okay, so what only 4 possibilities are there, and similarly in the case of 3, only 2 possibilities are there. So 4 possibilities times 2 possibilities, which is 8, and these are the number of divisors of 24. Sum of all divisors. Actually, this question is this question requires some concept of geometric progression also. Let we have to find the sum of all divisors of 24. Let's take some another number, say 248. So first we will do its prime factorization. That is 2 1 2 4, then 2 6 is 12, 2 2 is 4, then 2 3 is 6, 2 1 is 2, and here we get 2 cube times 31. It's one of its random factor. In general, its factor can be written as 2 to the power I times 31 to the power j, where I has the possibilities 0, 1, 2, 3, and j has possibilities 0 and 1 only. For all these possibilities, we have to find its sum. So summation I is equal to 0 to 3 and summation j is equal to 0 to 1. It can be done like this. After applying the concepts of geometric progression, we will get 2i plus 1 minus 1 over 2 minus 1 multiplied by 3, actually not I plus 1, it is 3 plus 1, and 31 to the power 2 plus 1 plus 1 minus 1 over 31 minus 1. And for more detail, you can visit the question given in the I button, that how we are applying the concepts of GP here. Some of the numbers formed by n digits. Say we have certain digits given like 2 3 7 8 9. We have to form different numbers from these digits like 2 3 7 8 9, 9 7 3 2 8, 2 3 8 9 7, and in this way we have to find all the possible numbers and then we have to add them. In how many ways we can do it? How many numbers will be there? In there we have 5 factorial numbers, right? Why? Because 5 factorial permutations of these numbers are possible. Now if we look at the ones place only, in this one place several times 9 occurs, several times 8 occurs, many times 7 occurs, 3 occurs, 2 occurs, but occurrence of these numbers will be the same. Means number of times 2 occurs is equal to the number of times 3 occurs is equal to the number of times 7 occurs, number of times 8 occurs, number of times 9 occurs, these will be the same. Means average of the numbers which are on the ones place will be equal to the average of these 5 digits. Means 2 plus 3 plus 7 plus 8 plus 9 over 5. Great. Now if average is this and total numbers are 5 factorial, then the sum of ones place is equal to average multiplied by 5 factorial. In this way, sum of tens place is equal to 10 times the sum of the ones place, means 10 multiplied by average multiplied by 5 factorial. Similarly, we have hundredth, then thousandth, then 10,000th place, means the total sum is equal to 1 2 3 4 1 2 3 4 okay 10 to the power 4 plus 10 to the power 3 plus 10 to the power 2 plus 10 to the power 1 plus 1 multiplied by average multiplied by 5 factorial, which can be written like 10 to the power 5 minus 1 over 10 minus 1 multiplied by average multiplied by 5 factorial. This is the sum of GP. We are using the sum of GP. A 1 plus R square plus so on up to R to the power n is equal to R to the power n plus 1 minus 1 over R minus 1. We are using this formula to write to go to this step from this one. Here the direct formula is written that sum of do the sum of digits, then upon the number of digits, n is equal to number of digits here, and then find all the number of permutations, then 10 to the power 9 minus 1 over 9. Here n is equal to 2. Why? Because there are only 2 digits. Here n is equal to 4, means every time the digit is repeated, it should be counted. Try these questions yourself. Division into groups. Let's start this topic by taking an example that what kind of questions are there in it. In how many ways two teams, one of 6 and another of 4 players, can be made out of 10 players? We have 10 players and we have to make one team of 6 players and another team of 4 players. Okay, so if from these 10 players we select 6 and make a team of those 6 players, then the remaining 4 we don't have to do anything from the remaining 4. The remaining 4 will automatically come into another team. Okay, so how many possibilities are there? There are 10C 6 ways to do this. Or if we select 4 first, then also we will get 10C4. So are these different? No, values of both are same. Let's take one more example here. In how many ways 3 teams of 5, 6 and 9 players can be made out of 20 persons? So suppose you can see that 5 plus 6 plus 9 is equal to 20. So if we first select 5 out of 20 and put them in team 1, then if we select 6 out of 15, why? Because 5 are already selected, so rest remaining are 15. 6 out of 15 and put them in team 2. Then we don't have to select anything. The remaining will be automatically in the team 3. We can do this thing in any sequence. We can select 6 first, then 5, or we can select 9 first, then 6, then 5, or just any sequence. We will get the same result. So here we have 20C5 times 15C6 possibilities. It is equal to 20 factorial over 5 factorial times 20 minus 5 means 15 factorial multiplied by 15 factorial over 6 factorial times 15 minus 6 means 9 factorial. 15 gets cancelled out and in the end we have 20 factorial over 5 factorial times 6 factorial times 9 factorial. Notice a thing that we had to make team of 5, 6 and 9, and in the denominator we are getting 5, 6 and 9, all of them. No difference is created between these 5, 6 and 9. But in up to the questions which we were discussing, there was no definite sequence of selecting them. But if the selection of the sequence also matters, then we will have to multiply them with 3 factorial. Look at this question. In how many ways out of 20%, 3 teams of 5, 6 and 9 players can be assigned to 3 coaches? So suppose there coach 1, coach 2 and coach 3. To coach 1 we have to assign a team. There are 3 possibilities. We can assign him a team of 5, or we can assign him a team of 6, or we can assign him a team of 9. So this time if we select a team of 5 players first, then 6 players, then select 9 players, and in the second way if we select a team of 6 players first, then a team of 9 players, then a team of 5 players, then all these 3 cases will become different, because if we select 5 players first, then the coach 1 will get the team of 5 players, and if we select 9 players first, then the coach 1 will get the team of 9 players. So this time total possibilities are 3 factorial multiplied by 20 factorial over 5 factorial, 6 factorial, 9 factorial. Okay, I hope the difference is clear. So now here is the generalization for this. Number of ways in which n groups of p, q, r things can be made out of p plus q plus r things when order is not important is p plus q plus r factorial over p factorial times q factorial times r factorial, and when order is important we just multiply them by the factorial of number of groups. But if p is equal to r p is equal to q, which is equal to r, and in this way all the n groups contain equal elements, say all these are equal to m, then in this case things get something different. Means if we put m in place of p, q, r, we will not obtain the required result. Look here, if we substitute, then we p equal to m, q equal to m, etc., then we will get mn factorial over m factorial raised to the power n. But we see that there is an extra n factorial in the denominator, and similarly when the order is important, this n factorial is absent here in the formula. So why it is so, we will discuss it. Say there are 4 elements and we have to divide them into equal groups. So equal groups of, suppose equal groups of 2, we have to make 2 groups. Okay, so what strategy we follow? We select 2 and put them in group 1, say G1, and then remaining in group 2, say G2. So what can we select? We can select 1 or 2, sorry 1 and 2, and 1 and 3 we can select, 1 and 4 we can select, 2 and 3 we can select, 2 and 4, and we can select 3 and 4. When we select 1 and 2, remaining will be 3 and 4. When we select 1 and 3, remaining are 2, 4, then here 3, 2, and 1, 4, 1, 3, and 1, 2. But since order is not important, and here we see that we have made 2 groups, 1, 2, 3, 4, and in the last row also there are groups of 3, 4 in one and 1, 2 in the another. But since order is not important, means these 2 cases should be treated as one, order not important, and that is why the number of obtained divisions should be divided by 2 factorials, means the number of factorial of number of groups. This thing doesn't occur, this confusion doesn't occur when we divide the things in unequal number of groups, means groups containing unequal number of elements. Like suppose we have 5 elements, 1, 2, 3, 4, 5, and we have to make 2 groups, one group of 3 element and other of 2 element. So if we have 1, 2, 3 in the first group, then in the another we will have 4, 5, and there is no chance for the confusion of this ordering. Why? Because order means order cannot repeat, because first will always contain the 3 and another will always contain the 2, so there is no possibility of repetition. That's why this 2 factorial is not important in this case, as we have just seen the formulas. So here 2 questions for you. If you got the concept, you will be able to do this. Divide 52 cards into 4 equal groups and distribute 52 cards into 4 people. Now distribution of n identical objects into r different groups. Suppose we have n identical stars, and then we have r different groups, and we have to distribute these stars into these groups. At first it seems easy. Let how many possibilities this star has, in how many groups it can go? It has r possibilities. It can go in the first one, it can go in the second one, then in the third one, and so on. And there is no restriction, like the one group cannot contain more than one element or less, or no element. No restriction is over here. So another one can also go in r groups. Another star can also go in r groups. But wait, we are doing something wrong. What wrong we are doing? Let us see. First we said that first star can go in any of the group. So suppose for some time, suppose that first star go in the first group and second star goes in the second group, and we have taken this in consideration in our r times r. Okay, next possibility is that first star go in the second group and second star goes in the first group. This possibility is also taken in consideration in this one, but since the objects are identical, both of these cases will be treated as the same, and that is why this approach which we were going to apply is wrong. So we cannot do it like this. This question is understand with a famous explanation of star and bar arrangements. Suppose we have let's take some simple example. Suppose we have 3 stars and we have to divide them into 2 groups. uh, 2 groups. Okay, so how can we do it? If we take a bar like this and then put it somewhere in between or in the right or in the left of these stars, then apparently this bar will divide them into 2 groups. Like suppose bar is kept here. In the second case, bar may be kept here, or the bar may be kept here or here. In the first case, group 1 contains 3 stars and group 2 contains only 0 stars. In the second case, group 1 is containing 2 stars and group 2 is containing 1 star. In the third one, group 1 is containing 1 star and group 2 is containing 2 stars. And are these cases repeated? Actually no, these two will be treated as different, because we are talking about different groups. Different groups means sequence is important here, so we will not divide them by 2 factorial or anything like that. This is how we do it. So when we had to divide it into 2 groups, we taken 1 star. Similarly, if we have to divide them into, say some stars are like given here, and we have to divide them into 3 groups, then we will need 2 such bars. And in the similar way, when there are n stars and we have to divide it into r groups, we will need r minus 1 bars. Okay, r minus 1 bars. Now we have to find the permutations, total number of permutations of stars and bars taken together. Like there are so many stars kept over here and so many bars kept over here. There are n stars and r minus 1 bars, and we have to find their total number of permutations. So how many permutations are possible? N plus r minus 1 factorial over n factorial times n plus over r minus 1 factorial. Sometimes it is given that there should be at least one element in the group, means no group should be empty. So if we have n stars and r groups, then at first we keep at least one star in each group. Okay, now still we have to distribute some of the stars in r groups, but number of stars this time are n minus r, because r stars are already distributed, and the question is changed to distribute the n minus r stars into r groups, r different groups. So it can be done like n minus r plus r minus 1 c r minus 1, and r get cancelled out and we get n minus 1 c r minus 1, which is written in the formula. Now if we take arrangement also into the consideration, then the problem becomes like all the stars are different. Means we were taking that the at first before this we were taking that the identical objects should be distributed into different groups, but this time objects are not identical. This time objects are distinct, and their order also matters, but our bars are still the same. Bars are still identical objects. So this time when we will do their permutation, when we will find their permutation, we will get n plus r minus 1 factorial over r minus 1 factorial, and this is equal to n factorial multiplied by n plus r minus 1 c r minus 1 written over here, and in the similar way the next case may be obtained. With the help of these concepts, number of integral solutions of an equation like these can also be obtained. Suppose x1 plus x2 plus x3 up to xr is given equal to n, and we have to find the number of possible solutions of this equation. What does this mean? Means suppose 1 plus 2 plus 4 plus 0 so on, like 4 again element may be repeated also, is equal to n. This means 1 2 4 comma 0 and so on to 4 is one of the solution. Okay, similarly if 2 plus 3 plus 5 and so on gives n, then 2 3 5 with the other numbers is another solution, and in this way we have to find the all possible solutions. We have to find the number of all possible solutions. It is written that integral solution, that's why we are taking only 4 and 2 etc. We are not taking 2.1 2.3 etc. Okay, how can we find this? We have to think it like isn't it that x1 x2 x3 are like different groups, and x1 x2 x3 can be supposed as different groups. These are the different groups, and we have n identical objects here. N identical objects have to be distributed in r different groups, so it can be done in n plus r minus 1 c r minus 1 ways, and these are the number of integral solutions which are possible. If this was the case for the non-negative. If we take positive, means we can not take any of the xi as 0. In x1 x2 x3 none of them can be 0, means at least the minimum possible value of any xi should be 1. So let's first distribute 1, and in this case the question is converted that no group should be empty. In the case in which there was that no group should be empty. So n minus 1 c r minus 1 are the number of integral solutions in this case. Find the number of integral solutions, find the number of possible solutions of x comma y comma cut. Find the number of possible solutions of x, y, z is equal to 48, where x, y and z are natural numbers. 48 can be written as 2 times 2 times 2 times 2 times 3, which is equal to 2 raised to the power 4 times 3 raised to the power 1. Okay, now we have to make an x, we have to get an y, we have to get a z, such that their product is equal to 48, and then we have to count all these cases one by one. X may contain 2 with some power and 3 with some power. Similarly, y may contain 2 with some power and 3 with some of exponent, and similarly there is z. Great. Now if we talk about the exponent of 2, then here exponent in the x, exponent of 2 in the y, and exponent of 2 in the z, together it should give 4, means the sum of the exponent of 2 in x and y and z should be 4. So this is the question, something like that x1 plus x2 plus x3 is equal to 4, means distributing 4 identical objects into 3 groups. In how many ways it can be done? It can be done in 4 plus 3 minus 1 c 3 minus 1 ways. Now similarly, if we talk about the exponents of 3, then their sum in all of them should be 1. It is equal to, this is equivalent to x1 plus x2 plus x3 is equal to 1. So it can be done in 1 plus 1 minus 1 c 1 minus 1 ways. Sorry, 1 plus 3 minus 1 c 3 minus 1 ways, and these will be the number of integral solutions of this equation. Application of multinomial expansion. It's an interesting concept. Here we will learn how a multinomial expansion can help us to deal with some of these problems of permutation and combination. Suppose we have an expression a plus b plus c multiplied by p plus q plus r multiplied by x plus y. When we expand this expression, we will find terms like a p x plus a p y plus b p x, and in this way other terms like c r y, like b q x, etc. In this each term, one of the factor will be from the first bracket, another factor will be from the second bracket, and another factor from the third bracket. You can see a is from the first bracket, b from the second one, and y from the third one. Here also c from the first one, r from the second one, and y from the third one. Okay, this much is clear. Now if we have an expression like 1 plus x square and so on up to infinity, an infinite series multiplied with another infinite same series, a1 plus x square, so on up to infinity. Okay, here also the terms will be like this, that the first one is from the first bracket and another from the second bracket, but this time there are not many variables. There is only one variable x, so the series will contain 1 plus a constant time x plus a constant time x square plus another constant time x cube and so on. But if we have to find, suppose we take x raised to the power 7 in the consideration, let us see what can happen. How we can get x raised to the power 7 and what will be its coefficient. If we multiply 1 with x raised to the power 7 in this bracket, term will be like this: x raised to the power 0 and x raised to the power 7. Similarly, x raised to the power 1 multiplied by x raised to the power 6 plus x raised to the power 2 multiplied by x raised to the power 5 and so on, which on addition will give us some coefficient multiplied by x raised to the power 7. This coefficient is helpful for us. How? What does this coefficient represent here? If we look that, then indirectly we are writing all the possible ways in which all the possible ways of x1 plus x2 equal to 7 can be written, means all the possible integral possible solutions of x1 plus x2 is equal to 7. So this coefficient represent all the number of possible integral solutions of x1 plus x2 is equal to 7. Similarly, if we take another series, series like 3 series in multiplication with each other. Okay, as when we take this, suppose we have to find x1, we have to find the solution of x1 plus x2 plus x3 is equal to 9. So in this case, coefficient of x raised to the power 9 will be the number of possible solutions of this equation, number of possible integral solutions of the equation. Now in general, if we take x1 plus x2 plus x3 and so on up to xr equals to n, we have to find its solution. So it can be written like 1 plus x square and so on multiplied by 1 plus x square and so on multiplied by 1 plus x square and so on r times. So it is equal to 1 plus x square raised to the power r, which is equal to 1 over 1 minus x raised to the power r, the sum of infinite GP, which is 1 minus x raised to the power minus r, and it can be written as 1 plus r c1 raised to the power 1 plus r plus 1 c2 raised to the power 2 plus r plus 2 c3 x cube and so on, and coefficient of n will be coefficient of x raised to the power n will be x plus will be r plus n minus 1 c n, or we can write it also equal to x plus n minus 1 c r minus 1, and this was the formula which we had just derived also. This multinomial expansion can also help us in another way, like if some restriction is given to us. If there is a restriction uh, like x1 lies between 2 and 5. In this case we make a modification in the series. In the first bracket we write x square plus x cube plus x raised to the power 4 plus x raised to the power and 5, that's it, and remaining will be the same, and this time the coefficient of the required number will give us the required solution. Exponent of a prime number in n factorial. Let's take an example, say 15 factorial. 15 factorial means 15 multiplied by 14 multiplied by 13 multiplied by 12 and so on up to 3 multiplied by 2 multiplied by 1. If we do the prime factorization of 15 factorial, then it will contain some power of 2 multiplied by some power of 3 multiplied by some power of 5 multiplied by some power of 7 and so on. Now the question is to find the power of 3. Say we have to find that what will be the exponent of 3 in the prime factorization of p factorial. So at first it seems easy. Let's just identify all the numbers which are the multiples of 3 which are present in the 15 times 14 times 13. So here from 15 we will obtain the 3. Okay, so one contribution in the exponent of 3 in the prime factorization of 15, another contribution from this 12, another contribution from this 3. So in total 15 upon 3 means 5. This sum will give us equal to 5. So is it the required answer? No. Here there will be a case when the number will contain more than one as an exponent of 3. Means suppose there is 9, then 9 will not give a contribution of 1. 9 will actually give a contribution of 2, right? 9 will contribute 2. Why? Because 9 is equal to 3 square. So instead of identifying the elements with different contributions, let's just add 1 for the 9 again in the next row. It is equal to 1. So in total we get 6. In prime factorization of 15, exponent of 3 will be 6. Let's take a larger number to get the concept. Suppose we have 100 factorial. 100 factorial means 10 multiplied by 100 multiplied by 99 multiplied by 98 and so on up to 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and we have to find the exponent of 3 in the in the prime factorization of 100. So we will get one contribution from 99, another from 96 somewhere here, and in this way so many numbers will give contribution of 1. Then we will add 1 for each of them. How many ones will be there in this row? There will be 100 over 3. Greatest integer less than 100 over 3. Great. Some of the numbers like 9 which will be present in between somewhere here and 27 present somewhere between here will give us contribution more than 3. So for them we will add 1 more. So how many of the numbers will give a contribution more than 1? It is 100 by 9. So we will add 1 for each of them, like 1 for 9, 1 for 27, and so on. Then there will be some numbers which will give a contribution of more than 2 also. So for them again we will add 1 for each of them, like 27. Like 27 is equal to 3 cube. So it is giving a contribution more than 2. So for them also in the next row we add 100 over 27, greatest integer function of 100 over 27, and then there will maybe numbers which give contribution more than 3 also. For that we take 100 over 81, and in this way after finding all this, and after limit means if we take 100 over 243, then it is equal to 0. So taking more rows will not affect anything. So in the last we will have to add all these. If you want to understand it with one more example, you can get a link in the I button. Now few of the subtopics of permutation and combination are left, which will be covered in the third video along with the examples of different types. Please tell us in comments if you want us to add something for the upcoming videos. Please share these videos with your friends who want to study or revise the topics. If we get a better response from you, we will try to upload the videos more frequently. Thanks for watching.